All right. All right, hey, we don't have a warm-up problem to get started, just a little pulse check today. So fill in the Slido for your little extra credit point. Yes. We're going to get started because I'm sorry, I do have a lot to get through content-wise today. But feel free to fill out that Slido. It's just a little pulse check. Reminder, of course, we do have an exam here in this room a week from today. We will formally start the exam at 3:35 because I know it takes people a minute to get here. We will end the exam at 3:25 because nobody's in this room after us because we can. Shout out to Simon, one of our wonderful TAs, who was like, wow, there's no practice midterms that look like this midterm, so I'm going to write you one. So shout out Simon for doing that. For all of you, yeah, for real, y'all. And so it's here. Thank you. Our hero, yes, above and beyond. So there you go. It's posted on the course website, so you can get a sense of what it's going to look like, what the format's going to be. Please feel free to take a look and ask us any questions on the ed board. I know I sort of chatted about topics and things like that on Wednesday, and we did a brief little review of run times, but does anyone have any questions about the exam at this moment in time? Okay. And then, of course, as a reminder, Project 2 is due next Wednesday. Shout out to those of you that are getting started. I had a bunch of really wonderful conversations in my office hours on Wednesday about how to get started. Understanding all of the different pieces of this are complicated. This is not an assignment that you should do within 2 days. It's a 2-week assignment for a reason. I swear, please just read it. Just read it so you can ask us questions. Otherwise, next Wednesday is going to be so uncomfortable. But if it happens, we'll still be there to support you. But please, get started. I swear, that iterator, it will melt your brain. You don't want to be doing it all in one go. Let's take a look at what our feelings are in our Slido. Oh, look, I was trying to use, wait, that's not what I'm looking at. Okay, also, real talk, I tried to use ChatGPT to help make these slides because there's not good online stuff. ChatGPT's code was wrong. ChatGPT does not have correct code for left-leaning red-black trees, just so you know, so don't plug it in. I looked. Wait, where am I going? This is what I'm doing. That's how desperate I got. I was like, I can't find it on the internet. Yeah, well, there you go. How are we feeling? Aha, yes. Vibes. Yeah. Mildly stressed. Nervous. Oh, no, didn't know there was one. Okay, hopefully you know now. Talking about it a bunch. Cool. But look we're all in the same ship together. Is it annoying that I still have to do assessments? Yes, I swear I'm trying so hard to figure out how we don't have to do these silly things. But remember, you get the redo option. So after you receive your grades, you will get to resubmit all of your answers, and we will grade them exactly the same way that we graded it the first time, and you can make up to your half your points back. So even if you have a really bad day next Friday, you can still end up getting a pretty good grade. So, yeah, but there you go. All right. So, let's dive back into it. This is sort of where we left off. Okay, and first, here's a caveat. Y'all, I apologize. I swear, every year I try to adjust this class a little bit, and if you couldn't tell, part of the ways I adjusted this class was to take out a lot of the math. I was kind of mentioning that, but I was like, what do we replace the math with? And red-black trees is this is the first time we've ever done this. And I wasn't quite sure how to make it easy for you to learn. I now have some slides, so I'm sorry it was a little between last lecture and this one. But I promise, literally after these lectures, we're just getting back into the regular rhythm of things, and things will feel much more like I've taught them the exact same way multiple times. But the reason that I taught these 2-3 trees is because actually I think they help because it's every 2-3 tree can be translated into a red-black tree, and I'm going to show you how to do that today. And I kind of think the 2-3 trees are a little easier for our brains to initially grasp. So that's why I was forcing you to do these. So if you remember, with a 2-3 tree, we have two different types of nodes. A 2 node, which is 1 data point, 2 connections. A 3 node, which is 2 data points, 3 connections. And so we can just add things in. This here is the final form of adding those values. And you can see that every time we add a new value, 1, we add it to a leaf node. 2, if we've overloaded a node, we split the node and push things upward. And so what this does is this maintains the height of the tree. That's the sort of self-balancing goal here, where we've got this sort of idea where we're doing everything in our power to not add a new level to the tree. So that's sort of the basics behind the 2-3 idea. So that does give us a worst-case logarithmic runtime, which is the goal of any balanced tree. So it's got that same complexity class worst-case runtime as the AVL tree, which is nice. The other thing that's cool about the 2-3 trees is that we don't have to do any of those complex rotations. I think I flashed the code at you on Wednesday, and I was like, look at how gross this is. It's like linked lists, but more. We don't have that necessarily in 2-3 trees. I'm going to show you some of the code. And technically, we get a little bit better of runtime because of the constants of dealing with arrays instead of nodes. But we have these rules about how we split the nodes, but we don't actually have these rules about maintaining a specific height or a specific balance. We just sort of get those as benefits by doing this sort of oh no, the node's overloaded, rotate it or split it and send it up. So on average, a 2-3 tree can become a bit more imbalanced than an AVL tree. An AVL tree starts with the rules of balance, right? It's at most, the left and right tree can differ by 1. This doesn't have that rule. It's just ooh, if the node's full, split it and send it up. If it's full all the way up, start a new line. And so we get the height benefits, but sort of as causation of those rules, we haven't actually based the tree on height. So AVL has the strictest balance rules of any self-balancing tree. And because it has the strictest rules, the AVL tree will always sort of stay the most balanced, which means it'll always kind of have the most guaranteed best case runtime. Whereas the sort of constants in the 2-3 tree, it'll be a little more imbalanced on average, so it'll have a little bit slower runtime when we're talking about, for example, finds. And then also multiple nodes can cause some complexity. Here is the insert code for an 2-3 tree. And so you can see what's happening here is we have an array to store the keys and an array to store the children. And then we have a number that tells us what type of node this is. And then we just sort of have to loop over those things. We update the keys. So there's a lot of array stuff going on over here, which generally is kind of better constants than the nodal sort of solutions. And this overall, it took me a full 2 slides to cram every bit of code for the AVL rotations in. This all kind of fits nicely in this one slide. So this is an improvement as far as the complexity of implementation goes, but I'm going to show you a even simpler implementation of a self-balancing tree. That's where we're headed with the red-black trees after this. So, okay, great. We just went with that. So let's talk about this red-black tree. So a red-black tree has these sort of 5 requirements. 1, every node is either red or black. Cool. So we've got 2 different types of nodes, but they're all the same structure. It's actually just a Boolean stored inside the node, whether it's red or black. The root of the tree is always black. That's one of our rules. And then there can be no 2 adjacent red nodes. That means for any given red node, it cannot have a red parent or a red child. So you can see in our example red-black tree over here, we start with black at the top, we've got a red here, and then it switches to pull it back to black again for its children. So these children of this red tree could not be red. That would be a violation of the red-black rule, number 2. or number 3, sorry. And then here, this is like the red-black requirement for height. Every path from a node to any of its null descendants has to have the same number of black nodes. So this is kind of like saying every node has to have totally balanced left and right subtrees if you only count the black nodes. So there is kind of a height requirement here, but it sort of says we don't care so much about the red nodes. So you can see here we've got this sort of concept of black height where, 8 to 5, 8 to 19, 8 to 12, those are all like the same sort of height. And the red nodes we don't count in terms of height. So we have a height requirement, but we've got these nodes that sort of are exceptions to that requirement. So it will still maintain a balanced definition, but again, this is another situation where we've sort of like relaxed the height requirement. So overall, the red-black tree will stay a little less balanced than an AVL tree. But because we relaxed that requirement, I'm going to show you that we can do some really clever things with the implementation that'll make this implementation a lot nicer for us. So that instead of doing rotations at every single insertion, sometimes we can just recolor the nodes. And recoloring a node is a lot easier than moving a bunch of pointers around, is sort of the idea behind that. And then every leaf is considered black, just to kind of keep this red-black organization going. So here you can see on the bottom, here's some examples. So this here is not a valid red-black tree because the right subtree and the left subtree of overall root are imbalanced according to the paths. They're all black nodes, but we still have to maintain this concept of every path from a node to any of its descendants has the same number of black nodes. The path from here to its descendants is 2 black nodes. The path from here is 0 black nodes, so that's imbalanced. Same thing here. We've got 1 black node versus 0 black nodes. And then here we've got, you can see it violates property 3. We got 2 adjacent red nodes, which is not allowed. So those 4 and 3 properties are usually the ones that are violated by an insertion because, we sort of set these things ourselves. These are valid. So here we've got a nice balanced red-black tree. This is also a balanced red-black tree. Siblings can be red, like across the same level can be red, but, they'll have black children because null is considered black and they have a black parent, so that's okay. Yes, question? For the red-black tree that violates property 3, yes. Like this one? No, the one on the right. Yeah, if the one like at the very end, if that one was a black node, wouldn't that just look just like this one? I can see that. Yes. So that would then invalidate property 4 because the path from this node to null here has 0 black nodes between it, but here has 1 black nodes between it. So that's imbalanced according to property 3. So even though it goes back and forth between red and black, it's violating the height one as opposed to the node adjacent red nodes one. Yeah? In property 5, it says every leaf must be colored black. I'm a bit confused about usage of leaf here because the leaf nodes. You're right. In this case, and I did put this in here because this is like the language that people will use in terms of red-black trees, but thank you for pointing this out. This is different than the way we've sort of been referring to leaf nodes. That's talking about these null little leaves hanging off of here. Yes. So, this is a walkthrough of how the insertions go in red-black trees. I'm not going to ask you to program these. I know there's like a couple questions on your exercises about valid red-black trees and about like what might trigger a rotation or not. So I'm going to click through these so that you can answer those questions, but I'm not going to spend a ton of time going into the nitty-gritty details of how these rotations go. However, there's this great YouTube video, so maybe while you're doing your exercises, if you need a little more detail, you could watch that. I've also got the code in here if you want to dive in a little bit deeper. but I'm going to click through these slides in a speed that I think matches the level of depth I need you to understand for this class. I'm sorry if that doesn't feel like we're going as deep as possible into red-black trees. But for every single time we add a node to a red-black tree, there's sort of 4 different insertion cases. 1, we haven't added anything ever to the tree. And so if that's the case, we make that node black. That's like our big exception. Overall root is our exception. The overall root must always be black. Then we have these sort of cases 1, 2, and 3. And these are based on, 1, whenever we add a node initially to a red-black tree, it will start as red. And that kind of makes sense when we compare it to the 2-3 trees. Because remember with 2-3 trees, we always added it to that leaf. And we always sort of overloaded it so that it didn't initially grow the height of the tree, right? Like we always found a way to like stuff it into an existing node so the tree didn't get taller. And then we did the splitting and the blah, and then maybe that generated more things. But this is the exact same idea. By adding it initially as a red node and deciding not to count red nodes when we're counting height, it means we're adding this node in, and then we're going to fix the orientation, but it's sort of like our same 2-3 policy of every time we add a node, we're going to do everything in our power to avoid adding height to it. So we're going to start the node as red, and then based on these things, we've sort of chipped away all of the different possibilities, and there's very few cases you'll find where that node eventually becomes black and can contribute to height. I'm just going to briefly walk through them. So first is the node's uncle is red. Your uncle is your parent's sibling. So like if I'm adding Z, originally you could imagine this tree looked like this. A was red, B was black, C was red. I'm adding in Z, and Z is going to start as a leaf node. It's going to start as red. Z's uncle is the C, because it's my parent's neighbor, as you can see here. Since that's red, all I need to do is this act of recoloring. And we're going to specifically recolor the uncle and grandparent and like, oh, look, now we have that sort of like no red nodes are touching. That's nice. The act of recoloring is a rotation-free update. It also recolors so that we still maintain the same number of black nodes, so we haven't grown the height. So this is, again, like adding to the 2-3 tree. We're just overloading that node. We haven't extended the height, which is great. So this is like one case where we don't have to do rotations and the height doesn't grow, but we still get to add things in. Yes? If B is the overall root, then we might have to do some rotations, because this will apply recursively. So if it gets all the way up to there, that may have to cause some rotations. But that's our one exception. Thank you. Yes? So we're always adding red unless... Yes. Yes, it always starts as red. So like let's look at case 2, for example. If the uncle is black, and when we add the node in, it generates that sort of kink case, sometimes known as the triangle case, well then we are going to do a singular rotation. We're going to rotate the inserted node's parent in the opposite direction of the inserted node. So here's my Z here. This is the case that's represented over here. So A is my parent, C is my uncle, C is black. And what I'm going to do is I'm going to rotate so that I end up, there you go, with those. And then I am missing the next thing, but then I will recolor A to be black so that those things match up. Sorry, I'll fix those slides. Then we have the line case. This is another one where we are going to rotate the grandparent, and then we will recolor. So again, we've got sort of like my uncle is black, but I've generated this line where I put it in, and we do this nice rotation. You can see this looks very similar to when we do those rotations that we were talking about with AVL trees, because it is the same rotation as AVL trees. But again, this is a singular rotation. So both of these situations, instead of causing the double rotations that AVLs sometimes cause, we only at most have to do a single rotation. Like I said, I'm sorry, I'm not going to go into a ton of detail. You can watch the animations of how that actually works. But really, I just want us to get to this point where the reason that we care about these things, and actually the reason they were designed, is because AVL implementation was a pain in the booty. So a person invented this type of tree as a way to make it easier, so we didn't have to do the double rotation. Sometimes we just do a recolor. Sometimes we do a singular rotation. Because we don't do rotations all the time, and sometimes we just change the colors, which is literally just flipping a Boolean in the node, the performance on the constants is better in insertion and deletion for red-black trees. So for insertions, for AVL trees, because that's almost always going to generate either a single or a double rotation, even though that's a constant time performance, if we're just comparing the two constants, so we're within the same complexity class, but we're comparing the two constants with each other, red-black trees perform better in insertions and deletions. But that's because we've sort of decided some nodes don't count to height, so some nodes aren't going to like sort of trigger that same rotation. But that doesn't mean that when I'm going and finding things, I don't still have to traverse through those things. So AVL trees will still have better performance in the constants on lookup because they have that strict definition of balance. So this is our trade-off. We're trading off ease of implementation and runtime and insertion and deletions for a better runtime of lookups, though a more complicated implementation in AVLs. That's sort of the big takeaway with these sorts of things here. Any questions on that piece? We're going to go one level deeper. So actually, red-black trees are still kind of complicated to implement. In fact, the person that invented them, his name is Robert Sedgwick. He's a professor at Princeton. He invented red-black trees back in like 1978. If you go look it up, the way that Java implements tree map, for example, it's implemented with red-black trees. It was kind of considered the easiest implementation. But Robert, I think like in 2012 or something, was like, y'all still didn't understand. You're still overcomplicating the red-black trees, which is why Casey didn't want to force you to understand all of those rotations. So he came up with an even simpler implementation. That is called the left-leaning red-black tree. Those are the ones that are on your exercises. And they are truly just a translation of those 2-3 trees to get rid of the 3 nodes, where instead of having sort of red-black nodes, we now have red-black connectors. And when we translate those 3 nodes, where we've got like the 2 data pieces, when we sort of split those up, we're going to choose a preference for their orientation. We're going to prefer that the red connectors lean left. What I mean is, let's say we have a 2-3 node that looks like this, 4 and 9. This is a totally valid 2-3 node. You know, off to the left, I might have the values that are less than 4. Right here in the middle, I would have the values that are between 4 and 9. Right here, I would have the values that are greater than 9. I'm going to translate that into a left-leaning black tree by splitting this node, this 3 node, into two nodes, right? Which is a node with a singular value and maybe 2 children. And I am going to do so that the red connections only lean left. So this 4 and 9, here is a valid left-leaning red-black tree where 9's left child is 4. This is not a valid left-leaning red-black tree where 4 points to 9 as its right child. Though this is valid in BST, we're sort of choosing this preference of left-leaning. I'll show you the code and I'll explain why. But again, this is from your exercises. So we just talked about that one. That's not valid. We want it to lean left. This here is not a valid left-leaning red-black tree because, like the red-black trees we just talked about, we can't have the different heights from the top to the bottom of black connections. So here, This 3 node is imbalanced according to our red-black requirements of balance because there's 1 black connector to get to the nulls on the left, but there's like 2 black connectors to get to the nulls on the right. So this is an imbalanced tree. This would be a balanced red-black tree if I color these red, because just like where we were only counting the black nodes, now we're only counting the black connectors when it contributes to height. So it's sort of like this level here doesn't count. That's great. So now it's balanced. Cool. And then this is also not a valid left-leaning black tree because we can't have sequential red connectors. Cool. Yes? So, like the red arrows always have to be pointing to the left? Yes. Red arrows are pointing to the left. Good question. Cool. Okay. I'm pretty sure that covers all of the red-black questions on your exercises. So please feel free to ask questions on the ed board if anything comes up. Here is the LLRB insert code. But what I actually want you to look at is, do you see the lines that I have bolded? This is actually just binary search tree code. The bolded lines of code are the additions that turn it into left-leaning red-black code. There's literally only like, 1, 2, 3, 4, 5, 6, 7, 8 lines of code different. And this will still ensure a logarithmic worst-case runtime. Is it a little less performant on lookups than ABL? Yeah, but it's still going to maintain a definition of balance. It's still going to maintain a worst-case logarithmic runtime. I don't expect you to fully be able to implement this. I just want to show you how we've sort of chipped away at the complexity by sort of abstracting out our goals. Cool. Okay, that's actually all I want to talk to you about as far as self-balancing trees go. You've now met a lot of them. Technically, red-black trees and left-leaning red-black trees are kind of like cousins, but you've got like 4 of them now. There's a bunch more in here. The reason I teach you a bunch of different techniques for this type of stuff is because the goal of this class is for you to end up with a toolbox where you always appreciate that for every design choice, there's a trade-off. And if you understand the different tools, then you can always have options when it comes to those trade-offs. Here's some of the other ones. You can get real deep into it. It's a good time. This is a whole area of research if you're into this kind of stuff. Lots of fun things here. But does anyone have any sort of questions? I'm maybe going to pop over to the Slido in case anyone typed anything out. Yeah, scapegoat tree. I think I read that Wikipedia once. It's funny. Also, a lot of this exists because there's just researchers out there that are just trying to find different ways to do the same thing. And then they don't know how you'll use it, and it's your job to go find ways to use it. So that's how these things sort of explode. But let's take a look, see if there's any questions. Let's see. Oh, thanks. Thanks. Any other questions so far about red-black trees? Okay, great. So let's talk about our final type of tree. I'm going to say final tree, but surprise, we're going to see a new kind of tree on Monday too, but they're called heaps, so they deserve their own sort of category. But we are going to now meet the trie. So the trie is different than the other trees we've met. It is a specialized data structure, and what its job is to do is to store sequences of characters, very specialized. The other ones were just generic data structures. We could make them into a map, we could make them into a set, we could make them into just any way to store data. This is specialized. This is specifically for sequences. But the really fun thing about the trie is this realization that anytime you're trying to store a set of sequences, for example, a set of strings, and strings are a sequence of characters, well, you're probably going to have some strings that share the same sequences at certain parts. And instead of making an independent node for each thing, we're going to kind of reuse some of those branch nodes for similar entries. For example, this trie is a collection of these words, sap, sad, alls, a, same, sam. But we don't have to make multiple nodes for each of these S's and A's. We are actually going to, if you see here, we've got this node S followed by this node A, and then it branches off from there, and you can see we've got D, M, and P, and those are colored a different color. The way to read this trie is that, okay, this is a branch node, S, this is a branch node, A, and then this is a sort of entry node, D. It's colored purple, and what that means is that the entry, SAD, exists within my set. Now, instead of making a duplicate S and a duplicate A node, I can use that same S and A node and add an M child and color it red or purple, and that means I also have the entry Sam in my trie. I can do the same thing where I reuse S and A and I can add a P and color it. Now I've got SAP in my trie. So instead of having, how many would I have? I would have had, 9 separate nodes in order to represent those 3 words. Instead, I've reduced it down to only 5 nodes. So it gets really nice and compact. That's sort of the original goal for this. The other thing that's really great about this is that it's really quick and easy for us to find when there's patterns within the entry, when there's common prefixes in the entry. Also, this is sort of the logic behind, when you're, say, typing into autocomplete, and you like type in A, and it's like, oh, here's everything you could search for with A, and then you type another letter, and then it sort of reduces down the set, and then you type another letter. You can imagine what's behind that as a trie. That's sort of traversing through branches of the tree, telling you what entries are still available on that branch as you add in the sequences of characters. Google Autocomplete doesn't actually implement it with a trie anymore, but it did originally. But of course, they've further optimized it. I'm not going to talk about the crazy stuff they do underneath the scenes, but the concept still holds. It used to be really fun when I was like, this is how Google Autocomplete works, and then they changed it on me. But this was the original idea. Also, like phone trees, for example, if you start to type in, like the first 3 numbers of someone's phone, and they're like, oh, is it all of these, maybe? Also, usually a phone tree sort of implemented with this as well. So each level of the tree represents an index of the string. Yes, that's pretty much what we talked about there. Great. 2 ways to fail contains check. 1, if we fall off the end of the tree before we get to the last letter we are looking for, that means that the thing we are looking for doesn't exist. Or, if we haven't fallen off the end of the tree, but we land instead on our last letter on a white node instead of on a purple node, meaning we land on a branch node, not an entry node, that means that's not a valid entry. So Sam, right, we followed that path, we start with the first letter, S, cool. We start with the second letter, A, cool. We start with the third and final letter, M. It also happens to be a purple node, great. Sam is an entry in this trie, true. If we are looking for the entry of just SA, okay, well the S is there, great. The A is there, great, but that's my last node, and A is a white node, which means it is not an entry. So that would return false. A is both its first and last character, and it is a purple node, so that counts as a hit. That is in the collection. But if we look for SAQ, we would come down here, we'd say here's S, here's A, and then we'd be like, hey, there's no child Q. That's not an entry. I've sort of fallen off my tree. Or maybe I'm looking for the word samesies or something like that. I would come in, I'd be like, S, yeah, A, yeah, M, E, yes. And then if you're looking for the I that comes after that, I've fallen off the tree. That doesn't exist. That's not an entry. Does anyone have any questions on how to traverse the trie? Cool. Yeah, so this is a pretty fundamental difference that we've got this sort of concept where we're going to take the key and explode the key apart. This concept of atomic blob is like the key is itself, it's its own independent thing. We can't separate the key. I just treat it as a piece of data, and I only ever run .equals on it, for example. But this is specifically trying to recognize that we will have shared sequences within our keys to try and reduce the storage of our structure. Also, I know I'm showing you sort of like the Latin alphabet, but you could imagine this applies to any sequence of characters in any Unicode character set, or maybe it's sequence of binaries, whatever. I just use, Latin alphabet because that's the language I speak. But these come up in a lot of cases, and it's just about sequence of characters, not specifically strings. That's just the easiest thing for me to say aloud to you during lecture. Cool. Yes. Yeah. So there are technically different types of tries. We are going to be talking specifically about this type of sort of like sequence of characters from the alphabet, most of them. But as long as they hold a type of character, it's fine. Cool. Okay, let's talk about the implementation. So here is the ASCII table. I will also take this moment to point out and say the ASCII table, okay, actually out of pure interest, how many people have heard the term ASCII before? Okay, cool. How many of you have heard the term Unicode 8? Oh, wow, congratulations. You are far more advanced than most of the engineers that I work with, because most of the engineers have forgotten that there exists this whole other thing called Unicode 8, which is not quite so Western culturally biased. ASCII code is like English language and some other fun stuff. Unicode 8 is like, oh, the languages of many more countries. There's also more character sets, but you will find that a lot of the examples and a lot of the things were built originally with ASCII and haven't been adapted. I'm sure I don't have to tell some of you what it's like to try and type with a non-English keyboard into a lot of online services. And another moment to appreciate how important it is to think about this type of inclusive design at all phases of our software, because very few people did that for a very long time. And we all used each other's code. And now there's a bug in the code to bold words in Microsoft Office that's 35 years old and we can't change it. Crap like that. Okay, so here's a try implementation. So here is a node class. We've got the overall root, and you can see the overall root is sort of like a dummy node. Like it's just a place to start here. It's actually kind of similar to those bumper nodes that we made you use in the DEX assignment that are just sort of empty. It makes your code nice and clean, but they don't actually store any information in them. So then, from there, we have this sort of map of possible nexts. So this is actually an example of an n-ary tree, not necessarily a binary tree. Each node can hold up to however many characters are in your set as possible children. So if it's ASCII, I think it's like 256, something like 127, maybe. So every node could theoretically have 127 children to represent every possible permutation of every possible character in the ASCII set. So the way that we do that is instead of having separate fields for left and right, we have a collection that stores all of the possible references to my children. That's how you make an n-ary tree instead of a binary tree, where you just have one field, but it's a collection of however many children come after me. So each trie node needs to have up to as many children as there are characters in the set. Obviously, it would be a crazy set if it contains every single permutation of all of the characters, so that's going to be pretty unlikely. So, here we've got nodes with one child, and here's 3 children, and so on and so forth. Then we've got this Boolean is key. That means it's like one of those entry nodes. In our examples here, if that's true, that means it's like purple. That means like this is an entry in the set. And you can see here, we are generally going to use a hash map to store the children, because that's the quickest lookup. So what the lookup type in this hash map is going to be is the individual character, and the value is the reference to the next node. So A's hash map called next, A.get of D will return the address of this node D in it. A.get of M will return the address of this node with the M in it, so on and so forth. Any questions about that? It's kind of a different way to think about nodes. So, cool. Yeah. Yes. Yes. So each node, instead of having like a node left and a node right, it has one field. Its name is next, but that field is a hash map that could have up to, you know, however many characters in your set is the entry. Like if you were just using like English lowercase characters, like each one could have up to 26 or something like that. That's why a hash map's really important, because gosh, wouldn't it be a pain in the booty to have to like loop through all of those things? Thank goodness we know about these magical things called hash maps. So here's what it maybe looks like. Next points to a map. The map has maybe the value y is the key. The value points to the node whose character is y. It has its own next, so on and so forth. So it's this chain, a collection of collections of collections referencing nodes. Gosh darn, isn't that annoying when you have a bunch of nested objects? It's almost like that project 2, which I know has a lot of nested objects. Also, part of the reason we are teaching tries, I'm not going to lie to you, is because they come up in interviews a lot. They do come up in like implementation, like there are specific use cases for them, but it has become a very popular interview question. And because interviews love collections of collections, try is a really good one. Cool. Great. We looked at this. Great. Prefix matching. Okay. So this is sort of like the things that tries are exceptionally good at doing. And so, as you can imagine, since we are leveraging the same nodes, we can do this type of prefix match. So longest prefix of, that and find prefix, those are probably the two classic or canonic interview questions. But really what they're just asking for is like, hey, in this entry sample, what is the longest shared prefix with any other node? It's a really common one, and all it would mean is just like, hey, start down your path for sample and see how many nodes you find along that same path that share my prefix. So like Sam would be, for example, the longest prefix here. Yes? So for the longest prefix, this is starting to head towards that autocomplete thing. So like what it would be is, as you can imagine, as I'm typing things in, if I type in SAM, then I pause for a minute and Google does that little thinking thing and then it populates everything down. What it's really doing is traveling the tree, and then it's doing this sort of thing where it's like, harvesting, that's the word I was looking for, harvesting all of the key entries that branch off of that particular prefix. So if you type in like SAM and then it's like Sam, sample, Samantha, I don't know, those are the harvested keys that come after that shared prefix, which is really convenient for autocomplete. Yeah.
So here, a node can have many children, but a node can't have more than one parent.
Yes. So each node has one parent that can have however many characters are in your set children. Yes. So like, for example, you can see that there are multiple nodes with the entry S, like here's an S and here's an S, and like here's an A and here's an A. So it's not that you only have one node per character, but we are leveraging the prefixes specifically to hold that, like one parent, multiple children. If we didn't do that one parent thing, that would be a graph, which we're going to spend 3 weeks of this class talking about after the exam. Other questions? Cool. So yeah, prefix match, it's sort of this idea of prefix. How do we get the collection of things that all have the same start to each other? Cool. Yeah, so collecting all the keys in a trie or harvesting them, it really just means sort of traveling through the trie and building up answers based on those sort of entry purple nodes. So you kind of keep track of the prefix as you're traveling, and every time you hit a purple, you print out the prefix you've built up so far, plus that purple. That's sort of like your base case when you hit those keys. So yeah, create an empty list of results for each character, call collection helper, return, all that sort of good stuff. This would have a sort of like tree linear traversal because you're going to touch every single node in the trie. So you just have to sort of traverse through the whole thing. But if you think of the number of keys as n, there will always be fewer nodes in the trie than the number of keys, right? Because we can overload them. So in this case, we need to keep in mind when we're thinking about the runtime, not only how many keys there are, the value of n, but how long each of those keys are as well. Sometimes it's like s. So this now is going to start to force you to think about runtime where it's not just the number of entries, but the nature of those entries as well when you're considering runtime. Cool. Yes, they typically do implement either a dictionary, so like you could use this to implement a dictionary where, you know, words are your keys and maybe definitions are your values. It could also be a set. Often it is commonly a set like that. There's lots of different implementations. I showed you the hash map one because I think that's one that, based on what we've learned so far in class, that's a comfortable one for us. But there's lots of different ways to store the children. The children are just a collection. So whatever way you decide to organize that collection, you know, depending on your situation. And then, of course, they store sequential keys because that find prefix, find shared prefixes, that's really the key use case for this. And all of those are just ways to sort of get at that autocomplete style of problem. Any questions about tries? I'm going to pop over to the Slido in case there is anything. Let's see. Where is the value in a key kept? Good question. So the value in the key, you would imagine that in these nodes, if we were implementing a dictionary and not a set, that I would probably have a, like, if it's a is key, like if that was true, then I would probably also have a separate field value, and then I would return that value. If key was false, then that field would probably be null, kind of thing. Great. Any other questions? Okay, that concludes our trees section of the course. Come back on Monday where I will make what I just said a lie, because we're going to talk about heaps, which are technically a type of tree, but a very special one, a really useful one. If you have any questions about that exam, please let us know. Shout out to Simon for making those practice midterms. See you on Monday. Yeah. We already did that.